Hello viewers, in today's session we are going to see using limits for comparing orders of growth. Asymptotic notations are rarely used for comparing the orders of growth of two specific functions. Limit n tends to infinity, t of n by g of n is equal to 0 or a constant or otherwise an infinity. The first case implies that t of n has smaller order of growth than g of n. Second case implies that t of n has the same order of growth as that of g of n. The third case implies that t of n has larger order of growth than g of n. The first two cases means that t of n is in big O of g of n. Last two cases means that t of n is in omega of g of n, and the second case means that t of n is in theta of g of n. Now let's see the problems. The first problem is compare the order of growths of half n into n minus 1 and n square. Let's use this property for solving this problem. Limit n tends to infinity, half n into n minus 1 divided by n square, which is equal to limit n tends to infinity. We are multiplying half n inside the parenthesis. After doing that, we get half n square minus half n divided by n square, which is equal to limit n tends to infinity. We are taking half outside, half into n square minus n divided by n square. After simplifying that, we get limit n tends to infinity, half into 1 minus 1 by n, which is equal to, we are taking constant term outside of limit. So half into limit n tends to infinity, 1 minus 1 by n. Now we are going to apply limit inside the parenthesis. After applying that, we are getting value 1 by 2, where it is a positive constant. Therefore, the function has same order of growth. Therefore, half n into n minus 1 is in theta of n square. Now let's see the second example. Compare the orders of growth of log n base 2 and square root of n. Limit n tends to infinity, log n base 2 divided by square root of n, which is equal to limit tends to infinity. We are going to apply L'Hopital's rule. So log n base 2, the first derivative of log n base 2 we are going to find, and the denominator is going to be the first derivative of square root of n. So after doing that, we are getting limit n tends to infinity. The first derivative of log n base 2 is log e base 2 into 1 by n, and the first derivative of square root of n is 1 by 2 into square root of n. Now this log e base 2 and this 2, these two are the constant terms, so we are taking it outside. After taking 2 into log e base 2 outside of the limit, we are getting limit n tends to infinity, square root of n by n. Now if you apply the limit, we will be getting 0. Therefore, log n base 2 has small order of growth than square root of n. So we can use little o notation. Therefore, log n base 2 is in small o of square root of n. Now the third example is compare the orders of growth of n factorial and 2 power n. So limit n tends to infinity n factorial by 2 power n. Here in place of n factorial we are going to apply the Stirling's formula. So according to Stirling's formula, n factorial is equal to square root of 2 pi n into n by e whole power n divided by the denominator 2 power n. Let's simplify this. Limit n tends to infinity square root of 2 pi n into n power n divided by 2 power n into e power n, which is equal to limit n tends to infinity square root of 2 pi n into n by 2 power e whole power n. Now if you apply limit, we will be getting infinity. Thus though 2 power n grows very fast, n factorial grows still faster. Therefore, n factorial is in big omega of 2 power n.